Zoom record.
Recording in progress.
All right. Hey, everybody. Let's get started. We're going to do chapter 6 today, at least 6.1 today and 6.2. Chapter 6 is on discrete probability distributions. Okay. In 6.1, we will be doing talking about what a discrete random variable is. And let's just start off your notes for this section with the formulas you're going to want to have and stuff you need to know. Expected value. Goes by E of X. And it's the sum, sigma means sum, this is capital sigma, of X times P of X. And you'll see what I mean by that in a second. And the other thing you might care about is the StatCrunch commands, what we'll use. StatCrunch, we're going to do stats, calculators, and custom. The value that it asks for, that's your X data. And it will ask you for weights. That's your P of X results. Why is there a smudge? Now that sounds like the screen or the camera or something. It's a dark spot. Oh well. So we can start with what are random variables. So random variables are numerical measurements for the outcome from a probability experiment. We usually use capital X, big X, is usually for the category of outcomes. And little x, lowercase x, is the all the different possible numerical outcomes. When you're done with that, we'll switch to the next sheet. Anyone need that up longer? Going in 3, 2, 1, lift off. God, that little smudge is starting to bother me crazy. Is the camera? Or is, oh, that, I know how to check. If I move the camera, it should move the spot. And it doesn't move the spot. It's some lighting issue. Okay, maybe it's the light or the shadow from the camera. Okay, good to know. All right, so let's do like an example. What the hell is Mr. Jones talking about? So let's say Isabella already spoke today. We'll use Isabella. Isabella and I play rock, paper, scissors. RPS. Rock, paper, scissors. I can use big X. That can be used to categorize the number of times I win. But let's say we play 5 games. So the big X is the category, and that's the number of times I can win. All the possible outcomes that that X could be, I could never win, which would be 0. I could win 1 time, 2 times, 3 times, 4 times, and every time. The notation that we'll use when we're talking about the probability is going to be probability that big X, and we'll usually have that big X in there, equals little x, and we'll usually put one of the numbers in. So probability that x equals big X. What is the probability? What this is saying is, what is the probability that the number of times I win equals a specific or the specific value little x. Maybe I'll try to make those x's look definitely one's bigger than the other. Now it looks like that's part of it. Why don't I just do that again? There we go. Now one's definitely bigger than the other. So the number of times I win, the big X, this is called the random variable because the outcome is random. We don't know what it's going to be until we play. You will see me abbreviate that as RB from time to time because we'll say it enough. So we call this a discrete probability distribution. Because the outcomes are countable. And countable, what I mean by that, there's a limited number of them. We talked about this in chapter 1. We talked about discrete data versus continuous data. When we have continuous probability, when the data is continuous, we'll talk about this in chapter 7. So we'll get there, but chapter 6 is on discrete. And one more definition for you, probability distributions. They are generally tables that list all possible outcomes and their probabilities. All possible outcomes, these are that's my x, and their probabilities is the p of x. So we talked about those as being part of the expected value, and they'll show up in a second. Some things that are required for a probability distribution. Probabilities have to be less than 1. They can equal 1. They also have to be positive. They have to be greater than 0. Why is my shit tipping? There we go. That's my first requirement. We'll call it A so I don't see numbers there. And the second requirement is that the probabilities have to add up. Again, this is capital sigma, and it means add up. We have to add, when we add up all the probabilities, it has to equal 1. You guys ready for some more?
Can you give me like 15 seconds?
Yep, I can.
Okay, I'm ready. Thank you.
Anybody else? 3, 2, 1, lift off. So let's use an example. This will be pre-pandemic information. The number of movies streamed from Netflix. In a month can be given by the following probability distribution. Probability that x equals 0 is 0.06. Probability that x equals 1 is 0.58. I'm curious to see if they have the information available for what it is now. The pandemic kept a lot of people home. People wanted to be entertained, so they started watching shit like Netflix, Hulu, Disney Plus, stuff like that. I'll give you a second to write those down before we continue. Okay, so a couple things to note. Notice that all of these probabilities are positive, and all of them are less than 1. So 0 is less than p of x, which is less than or equal to 1 for any of the x's. And if we add them all up, we should get 1. Point 0.06 plus 0.58 plus 0.22 plus 0.1 plus 0.03 plus 0.01 equals 1. When we add them all up, the probability equals 1.00. That's what I mean by the sum of probabilities has to equal 1. Okay? Now, a lot of times we've been interested in mean and standard deviation. So let's talk about that here. The mean if we actually have data, individual data, I mean, we find x bar normally. Add them up, divide by n. Sum of x over n. In this case, we don't. We're just given the probability that the answer happens. This probably happened from collecting data, and they just found the proportions and said, okay, 58% of people watched one movie. So when we don't have actual data, Like this is actual data category. Actual. If we don't have actual data, we have to work on the theoretical value. And the theoretical value, we're using this summary of data, summarized data. And we will have that mu of x when we say mu of x, they list the random variable that they're talking about as a subscript, equals the sum of x times p of x.
I'm sorry, could you explain that again? That's for summary data, like data where you
Where
don't have.
we don't have the actual data. Like I don't know how many houses said we watched one movie. I don't know how many houses we had say watch 3 movies. This data has been summarized. Uh, Rather than just having house, you know what I mean? Going door to door, we would have actual numbers for each location, but we don't have that. So we don't have the individual data results. We're just given this is like a relative frequency distribution up above. So we don't have the actual data, we just have a summary of it. And I'll show you how to calculate. We're going to go up here and do these numbers. We're going to do this on these before I show you it in StatCrunch, because it's not too bad. It really isn't. Especially when it's small things like this. In fact, I'm going to give myself erasing stuff up there so I give myself some room to do it. Is everyone done writing this down? Okay. Let's come up here and calculate it. What I'm doing is I'm taking this value right here in the x row, and I'm going to multiply it by that value right here. I'm going to record the answer right here. 0 times anything is 0. 1 times anything is just the number. So 1 times 0.58 is 0.58. The rest, if you need a calculator, feel free to use it. 2 times 0.22 is 0.44. 3 times 0.1 is 0.3. I'll put 30 just so that I have the same number of decimal places. 4 times 0.03 is 0.12. And I got a 1 here, so anything times a 1 is that value. 5 times a 1 is a 5. And I got a 0.0 before that, so 0.05. That is my x times p of x column. Now, if I want to find the sum, I am going to add all these up. Mu of x equals all of these added. And I am getting mu of x equals 1.49. So prior to the pandemic, the average household streamed about 1.5 movies each month from Netflix. And we can see a bulk of that data is between 1 and 2, right? 0.58 and 0.22 covers most of the houses. And so our answer, it seems reasonable that it should be somewhere between 1 and 2. Does that make sense? Does that kind of clear up what I mean earlier by the summary?
I think it does.
Okay, good. That's what I wanted to hear. Lie to me if you need to.
For the third one, why did one side, like, why'd you get 0.22 and then the other side you got 0.44?
I am taking the 2 and I'm multiplying it by the 0.22.
Oh, okay, that makes sense. And then 0 is always 0, and then the 1, that's just the same thing. Oh,
Yeah,
okay.
yeah. And so like the 3 times, this is like 10 cents. 3 times 10 cents is 30 cents. 5 times a penny is a nickel. Yeah, it's multiplication.
And this would be your mean when this is like your mean, right?
This,
1.49.
this is the mean, yeah.
Got it.
And we don't, we're, since they did enough, they're saying this is the probability. We're going to say it's the mean for the population. And so what happens if we actually had data? If I can go up and write a little bit more. If we had actual data, the more results we have, or as n gets large, remember n is our sample size, then x bar, oh, that's calculus, x bar, and I'm off screen. Gotta look up every once in a while, make sure I'm on the right page, like you guys can see it. X bar is going to approach this value of mu of x. So like maybe when we have, if we had 10, it might be like 1.7, but if we did 30, we might be at like 1.55. It's quite possible that we jump to 50, it drops below 1.49, maybe drops down to 1.45. But as n gets big enough, we got enough things that we're adding up and averaging, we're going to get pretty close to 1.49. Another way of describing that is our average, the sample average minus the mean, gets close to 0. And I want to tell you guys a story. This is 100% true. Learning probability really well can pay you good money. This happened to me just last spring. I have a friend that works at Chuck Chansey as a pit boss. I think he's going to be a dealer trainer pretty soon. Before that, he wasn't with a specific casino. He needed some consulting work on probability. I got paid over $100 an hour to do a little bit of probability work, and I did it in Excel. I came up with the gambling payouts for a tournament at the casino in San Jose. It's called Club 8. It might be, I think it's Club 8. Club Infinity, Club Matrix. That sounds right. Club Matrix. I came up with the way to determine the payouts. I made $5,000 in less than a week. Just calculating the probabilities of specific card hands. Good money. It's awesome. So there is value in this. Are you guys done with this page? Okay. Okay. So we said, I'm off the screen. God, what was it? Matrix 8? Matrix something? Shit. I gotta look now. I'm curious. The dealer over at that Matrix, or the club, still emails me whenever he sees a good math comic strip he likes. He emails me, and he emails me every 2 or 3 months to let me know how they're doing. It takes, apparently, this was last year, like last March, like over 12 months ago. They still don't have the game in play because they have to get permission uh, from the state gambling office, whatever it is. And it apparently takes a really, really long time for those bureaucrats to get off their ass and do something, uh, which is crazy to me. Uh, so we had mu of x equals the sum of x times p of x. Okay, and so this is the mean value of a random variable. And it also happens to represents the value we expect to see in the long run. And since it's what we expect to see, we call it the expected value. So you will see e of x sometimes. It just means mu of x, and it just means the sum of x times p of x. And speaking of casinos, I will give you an example from a casino. Roulette. I'm going to safely assume not everyone has seen roulette. So I'm going to load up a roulette image so you can see what the roulette table looks like. Do a new share, make sure I'm sharing the whole screen. And we will go look up roulette. I'll do images. It's when you're in a casino, you see a little spin. This thing spins. The table spins one way. They spin a marble the other way. Eventually, the marble is going against the speed of the table. It slows down, and eventually lands in one of these holes. These holes are numbered between 1 and 36. They all have it also a 0, and sometimes they have a double 0. Like this one shows the 0 and double 0. Some tables, like if you've got enough money on the line, you'll find casinos that will have a table that only has a single 0. Okay, and then they have the roulette layout, the gambling layout. see if I can see an image where it just says, there we go. That's a good image. Then they have this playing field right here where you can bet on anything. You can bet on an individual number. Notice some of the numbers are red, some of the numbers are black. Green is all the zeros, and double zeros are always green. We're going to look at the double zero case. The math is a little bit different for single zeros, but I got it worked out for zeros already, or both zeros. Half of these numbers are red and half of these numbers are black. They don't alternate, although the first ones alternate red, black, red, black, red, black, red, black. When we get to 10 to 11, we got a couple blacks in a row. 18 to 19 is a couple reds in a row. So it doesn't just alternate red and black. That way there's some odd numbers that are red, some even numbers that are red. You can bet on any single number. You can bet on a row of numbers. You can bet on the first 12 numbers, second 12 numbers. Like you're betting as long as it lands on anything between 13 and 24, you win if you bet on second 12. If you bet on this top row, you win if it hits 3, 6, 9, any multiple of 3. And they also have the bets that are almost even. You can bet on the first half of the table, which is 1 to 18, and the second half of the table is 19 to 36. That's 1 to 18, 19 to 36. You can bet on even or odd, and you can bet on red or black. If they didn't have the zeros in there, this would be an even money game is what it's called. Zero-sum game. The odds of the house being ahead are not anything. But they pay out everything like there isn't a zero or double zero on the table. So let me show you what that looks like in terms of roulette payout. It can be a fun game, especially if you're betting on a single number and you hit, because the payout is really, really good. So we're going to go with, they say aught and double aught. That's 0 and double 0. And then there's 1 to 36. And we got done showing you, like half red, half black. Half are odd, half are even. So we'll look at the single player bet. A single player bet, or a single number bet, not single player, single number bet. It pays 35 to 1. What that means when we see a ratio like that, you win $35 if you hit. You lose $1 if you miss. And the reason why they do this is if without 0 and double 0, this would be even money. The way you can do the probability of one of these without the 0 and double 0 is generally the sum of these two values tells you how many options there are. 35 to 1 says 35 plus 1 is 36 options. So there is a 35 out of 36 chance you lose and a 1 out of 36 chance you win. That's without 0 or double 0. With 0 and double 0, it's no longer 35 plus 1. It's add in the 0 and double 0, it's 38 on bottom. And that means you lose on 37 because you only win on one of the numbers. This idea is normal ratios. When you'll see problems where this pops up. I literally added them up to do the division kind of thing. that doesn't apply in the roulette we're doing right now. This is outside roulette. 35 to 1 means 36. So let's make a probability payout table. Let's do our probability distribution. X and P of X. So let's say I bet on the number 13. I like 13. So if I hit the 13, if I hit or win, maybe I should do a column for description. Outcome. I win or I lose. So X will be the payout. And P of X will be the probability of said payout. So if I win $35. And if I lose $1. If I win, it happens 1 over 38. And if I lose, it happens 37 over 38. So I can write this as a decimal. Let's just figure out what this is. I'll do 1 over 38 first, and then I'll just figure out what that is. 1 divided by 38 is, I'm going to do a few decimal places because it's a low number. And then, so I don't have a good chance of winning. If I lose, I have a much better chance of losing. And I want to do 4 decimal places, so I'll stop there. So I am going to calculate my expected value. Because this plus 35 and minus 1, this is from the player's perspective. That's kind of important. The casino sees it definitely differently. If the player wins, they see it as a negative 35. And if the player loses, they see it as a plus 1. So what I'm going to do is I'm going to take these values right here and multiply by that. 35 times 0.263 and negative 1 times that actually is pretty easy. Negative 1 times that is just that value with a negative sign. I don't need a calculator for that one. But I do need a calculator for the first one. And I'm going to use the 1 over 38, not this rounded value. Times 35. Okay. So my expected value is when I add these up. In fact, since I'm talking about money here, these are dollar amounts, right? So my expected value is really what I expect to win. I don't really need anything past 2 decimal places. So I'm rounding, and they both happen to round just exactly they are. Nothing rounds up. So I'll just do 2 decimal places. My expected value when I add this up is negative 0.05. I can expect to lose a nickel for every dollar I bet. In the long run, if I play for a lot of time. Casinos frequently put caps on bets. You can only bet up to a certain max because they don't want someone coming in and betting $1 million and the player wins. They're happy if the player loses, but every once in a while, and it's since that if you've just played a single round, betting the like if you bet on even or odd, not just like a single number. If you bet on even or odd, or like red or black, you have like I don't know. Let's see, it's 18 divided by 38. You have a 47.3% chance of winning when you bet on one of the even money games. They don't like those odds for big money because someone's not going to come in and play $1 million 1,000 times so that the law of average or the long run can take effect. They're going to play once and walk out either $1 million ahead or $1 million behind. So they don't like that. The casino does not want to risk the chance of losing $1 million on a single play. Because then a player leaves. They do not keep gambling. You win $1 million, you walk out. The idea for the casino is no one walks out. Not ahead. They do have people on occasion, when it happens, they advertise it. So and so hit the keno or won the big money in something and won like 300. You'll see billboard signs on an occasion. Someone won so much money at Table Mountain Casino. Someone won so much money at Chuck's Hancy. They advertise the people that won a lot of money because most people lose. The interesting thing about roulette is it doesn't matter what bet you make on that table. Let's go back to the table. Doesn't matter if you bet the 2 to 1. It doesn't matter if you bet third 12. Doesn't matter if you bet on a single number or one of these even money ones down right here. These are the 2 to 1 is the rows. These values right here are also 2 to 1. And the values along the bottom are 1 to 1. Doesn't matter what you bet, the expected value remains the same for every single thing. The casino wins a nickel on every single dollar, which is crazy. In the long run, you got to remember it's in the long run. That's crazy. So what does that mean for us? Like expected value, what does that mean? So expected value was, I should do that. There we go. We found the expected value or the mean to be minus 5 cents. So if I want to see what I'm going to lose, let's say I play $10,000. Maybe $5 at a time. Maybe I'm playing $5 at a time, but I end up spending $10,000 in the long run. $10,000 times that negative 0.05 means I'm losing about $500. So I'll probably be at 9,500 after I bet around $10,000. Playing small amounts one at a time. I started with 10,000, I've lost 500. I'm down to 9,500. This is the idea of the casino. They keep you playing as long as possible. They generally don't show clocks, so you don't know what time it is. They generally keep a lot of the good games away from the windows, or the windows are darkened so you can't see daylight or nighttime outside. All you can hear is the action of other players. It's all an experience. Let's take a look at another type of example you'll see in this category, term life insurance. So a policy, life policy, life insurance policy, for an individual is worth 250,000. I'm just making these numbers up, but costs $530 annually. Up front. You pay for life insurance up front. The probability of an individual in whatever bracket this is, the probability of survival is 0.99791. Compute the expected value for the company. I'm pretty sure you have a homework problem that's similar to this. Give you a second to write all that down. And we're going to start making the table. So I will list outcome. That kind of helps me decide what X is going to be. We need a value for X. We need an area for P of X. And calculation for expected value. What two outcomes can happen from the life insurance policy's perspective? This life insurance company's perspective.
People either live or die.
People either live or die. That's fantastic. That's exactly what I'm looking for. So if they live, the company doesn't have to pay out any money. They just make a profit. They just make $530. If they die, they have to pay out $250,000. So you kind of want to think it's negative 250,000, but they got to keep 530 already. They already collected the 530. They don't give the 530 back. So like the net loss is 250 minus 530. and that's 249,470. Probability of survival is given. How can I figure out what the probability of dying is?
Could you subtract 0.99791 from 1?
Yes, that's exactly the way to do it. We know they have to add up to 1, so we should be able to do 1 minus the probability of living, and that will give us the probability of dying. Because probability of living plus probability of dying has to equal 1. So what is that? 1 minus 0.99791 is 0.00209. All right, now the fun stuff. I'm going to take these values and multiply by the x's. X times p of x. I've already got the 0.00209 in my calculator, so I'm going to start with the bottom one first. Times, I'm off screen, negative 249,470. And I get negative $521. Is that what it says? Yeah. And since we're talking about money, I'll do 2 decimal places. And if I do the other one, 530 times 0.99791, I get $528.89. So that when I add these up, it actually looks like subtraction because one's negative. When I add these up, it's $7.50. This is my mean, and this is my expected value for the company. So what does that mean to the company? $7.50 doesn't seem like a lot. But life insurance companies sell a lot of policies, don't they? If they sell 1 million policies, this average or this expected value doesn't work if they only sell like 50. That's too low. They're not going to make enough money. If someone dies, they're going to lose a lot of money. They need to sell a lot of policies. They sell 1 million policies. Each policy on average is going to pay them $7.50. 1 million times $7.50 is $7.5 million. That's after accounting for the deaths. Life insurance policy is a lucrative business. And we'll take a look at doing this in StatCrunch. Hopefully StatCrunch is working. Everybody ready? Does anyone need this up longer?
I do. I need like a few seconds.
Okay.
So why is X for dying? Why is that negative?
Because it's from the life insurance company's perspective. They have to pay out money. That's a loss in their book. So, and it's when they get to keep the money is 530. That's positive for them. So dying, they have to pay out the life insurance policy, and they don't like doing that. It loses them money. So our expected value is how much money they make on a policy. Does that make sense?
Yeah.
If they were
So
both
will
positive,
always
if they were both positive, it would show they expect to make 250,000 on every policy, and that's just absurd.
so will that always be implemented when you're calculating like X for a value? Like, does that make sense? When you are subtracting your given value from one, will it always be negative?
No, us doing this to find this 0.00209 has nothing to do with that being negative. If they had given us this, is that what you're asking? The subtraction is related to the negative?
Yeah.
No. If they had given us the death rate, we would have had to subtract this from this to get this number, and this is positive. So it just happens to be the data that we were given, the information we were given. That is an interesting question. No one's ever asked that. That's an interesting question. Yeah, they're not related. I can see why you would think that.
Can I see the word problem?
Yeah. All good?
Like 10 seconds.
Okay.
Okay, cool.
Cool. All right, let's go take a look at. Let's see if StatCrunch is up. Come on, you tricksy bastard. Okay, let's try this again. My math lab. And we will sign in. We will sign in. God damn, this sucks. While that's loading, let me look at the syllabus. See if we can adjust some schedule for today. Let's see. Oh, did I have something? I didn't finish posting it. Oh, that's calculus. Shit. I'm like, those aren't the right numbers. I think we can call it a wrap for today. And I will do 6.2 with 6.3 on Thursday. Let's see. And we might end up pushing 4.1 and 4.2 till after the midterm, which would be fine because it's not on the midterm. But since StatCrunch isn't working, I really don't want to like push this for you guys when a lot of the work you're going to be doing is in StatCrunch. There we go. Although I already said it. So we will stop after this section for the day. And we'll do 6.2 and 6.3 on Tuesday. So let's look at StatCrunch. And I'm going to use what we just did. This will be our term life. I'll call that X. I'll call this P of X, just so you can see it. And we're going to put in the values. We had 530 here. I had negative 249,470 there. I have 0.99791 here. And 0.00209 there. Let me see. Let me make sure they're all. I wish they did commas in here. They don't. Let's see the comma will be okay. Those all look good. So we are going to go stats, calculators, and although everything else on this category is in alphabetical order, custom for some reason, even though it starts with C, is at the bottom. So stats, calculators, custom. We will say the values are in X and weights are in P of X. And now we hit compute. And the graph isn't very helpful here, but notice the mean here, 7.5. So it tells us the mean that we're looking for. Okay, we could do another set if we wanted to look at the roulette. So I will call this payout. And we'll call this P of payout. That way when I'm picking from the table, it's easy to see. This was 35 and this was -1. And we had 0.0263 and 0.9737. When you have the values in there, stats, calculators, custom. Values are in payout, weights are in probability of payout. And we click compute. And we see that negative 0.05. You lose a nickel on every dollar you play. So the custom calculator will show you a lot of it. And I'll go back and look at the syllabus for a second, tell you how we'll do it. We will do 4.1 and 4.2 on Thursday, Tuesday, October 11th, and October 13th will be 8.1 and 8.2. They are both kind of short sections and can easily be put together, like shorter than normal sections. So we will do, we did 6.1 today. We'll do 6.2 and 6.3 on the 27th. And on the 29th, we'll do there's a 7.1 and there's a 7.2 also. 7.2 is really, really short. I don't even have it on the list here. We'll do those here on Thursday. We'll still have the review. We'll do a nice little review of what's going on in the class. And then your midterm will start in 2 weeks, basically. So, keep it up. You guys are good. I'm glad you guys are showing up, taking notes, asking questions. Is there anything else I can tell you guys about today?
Thank you. Good night.
Good night, Natalie. Anybody else? Nope. Everybody bouncing.
About it. Thank you.
All right. Take care, man.
You too. Have a good one. Oh, I have a question.
Yeah.
What are your office hours, if you have any? Do you have any office hours?
I'm in Zoom from 5:30 till or 5 o'clock to 6:30 on Tuesdays and Thursdays right before class, and I can always stick around afterwards. And I also will, if you ask over an email and say, "Can we make a plan?" I will work to meet with you.
Okay, yeah, because I usually get off at 6:15, so I'm getting here.
So if you want to, we can do questions after. And if you have questions right now, I'll stop recording and work with you.
Okay, yeah, I do. I have some.
Okay.
Recording stop.